Okay, let's get started. Okay. Yeah, I'm very sorry that it's for this late notice that we guys have to do this course online. Um because I just test positive, for the COVID-19. And I think I should be back to normal next week. If not, okay, we are going to continue the online course format, okay, next week as well. But I hope by that time I'm fully recovered. Okay. Um, so um, my voice may be a little bit low. Okay. Uh, uh, bear with me because I got a sore throat. Okay, so back to the course. Okay, first, I already have um the homework, the term project uh ready, but I haven't posted yet because of my illness. But I'm going to do it uh later today. Okay. And you guys can check it out and find a teammate to work with on the project. Okay. So um so last time we talked about uh the possible uh advantage of another possible advantage of the hierarchical um model. Okay. uh yeah um yeah, we talk about this result, right? If you for a group with only 1 point, okay, you know, if you try to analyze each group using a linear regression model, um, obviously that group has a problem. Okay, so instead, if we build a hierarchical model, okay, that group, even though it has only 1 point, it is able to get help from the hyperparameter of the other group, from the other group, okay, to restrict its range. So instead of, that wide, okay, now you can see the eighth group, which is shown by the alpha 7 and the beta 7. Well, it has, they still have like a wider range compared with the other groups, but that's caused by the single point data set in the group. But it is much better than if we do the analysis group by group, okay, separately. So this show you another advantage of the hierarchical model. Okay. And we can also draw the these lines, okay, the regression lines for each group, and by using this piece of code, and the result is shown here. Okay, so you can see that, okay, the last group, although it has only 1 point, but the posterior of the alpha and the beta basically suggests that, it has the similar trend uh, to the other groups, which is very reasonable, okay, considering that they are under the same umbrella. Okay. Okay. So I think I already explained. Okay. So um so this um correlation, causation, okay, are very confusing concept. Okay. So for example, okay, suppose we want to predict how much we are going to pay for gas or heat, okay, at our home, okay, during the winter, okay. In US, okay, for example, the gas and the I mean to heat up the house, I mean is expensive, okay, especially for states in the north part of the US, because you know US actually like the majority of states have snow in winter, okay. So if you don't have heat, okay, it's going to, you know, you are going to freeze to die to death, okay. So so this, okay, suppose, okay, we know, okay, the amount of sun radiation in the area, okay. This sun radiation, you can imagine, okay, if the sun radiation is high, okay, most likely the temperature will be up, will be higher, right? So it will affect the gas used for the heating, okay. So the gas price, the cost of the gas should go down, okay. So in this example, the sun radiation, okay, will be the independent variable, okay, which is X. And the bill will be the dependent variable or something that we are predicted, okay, which is Y. Okay. So we understand and we can explain this correlation, okay. But it is important, okay, to know that, okay, you know, we cannot, it's not like we cannot, you know, reverse the question. Okay, what do I mean is like you can predict the you know, the sun radiation by using the gas bill, because it is you know, simple linear relationship, right? So obviously if you can predict one from the other, I mean, mathematically speaking, you can do it, you know, the opposite way, okay, from Y to X, pretty much, okay. But you know, we call a variable independent because it's this value, okay, cannot be predicted by the model, okay. Instead, it is input of the model, and the dependent variable is the output, okay. So um, so we say that the value of one variable depends on the value of the other, okay. So this is, as I said, like this shows a correlation, okay. So the model basically build a dependency between two variables, okay. However, okay, we cannot say like this is a causal relationship, okay. I mean, in a linear model, okay. Folks, take the sun radiation as example, okay. Um, because causal relationship is much stronger, okay. The causal relationship says like X causes Y, okay. So you know, we actually have mentioned about this. Correlation does not imply causation, even though this mean, two variables may have strong correlation. Okay, they are not, no, their relationship, is not a causation. Okay, take this gas bill and sun radiation as an example. Okay, so we know, okay, we're able to predict the gas bill of a home, okay, from the sun radiation. Okay, and also the vice versa. The sun radiation, okay, can also be used to, to predict the the gas bill, okay, of our home. Okay, as I said, we can build a simple linear model between them. Okay, however, okay, it is true that higher sun radiation can be related to a low gas bill. Okay, I mean, it isn't true we can control the amount of radiation, okay, by changing the thermostat. I mean, basically the thermostat control like how much gas you want to spend to heat up the house. Okay, so if you change the thermostat of the house, okay, it's not going to cause the sun radiation emitted by the sun to change, right? Okay, if it's like a causation relationship, okay, then changing one can cause the other one to go up or go down. But in this case, changing the spending on the gas bill doesn't affect the sun radiation, right? So yes, they are correlated, okay, but no, I mean, these two things are not a causation relationship. Okay. So you could say that causation is more than correlation. Okay. Because to establish causation, not only you need to observe correlation, but also you need to find the physical mechanism that one variable affect the other. Okay, if you can do that, then you can claim a correlation is a causation. Okay, here I mean we can show you some interesting example. Okay, from this one moment. Let me show you another. Where is it? This one. You guys can see like this page, right? Okay. Not this one, not this one, sorry. Where is it? This one, this one, this one. Okay. So you see some very interesting correlation, but they are obviously not causation. For example, the first picture depicts like the US spending on science, space, and technology, okay, versus the hanging suicides, okay, in US. When US spend more money on the suicide, okay, sorry, on the science, space, and technology. I mean, interestingly, there's a coincidence that the number of suicide by hanging, strangulation, and suffocation also increase, and they actually match pretty well, right? But can you say that, you know, the 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 spending on the science, space, and technology increase? I mean, the cost the number of like people, suicide by hanging. It it doesn't look right. So another example, okay, this is number of people who drown by falling into a pool. Okay, basically like it's the people who drown, okay, by in the water. Okay, this is one variable. The other variable is the films Nicolas Cage appeared in. Okay, and interestingly, okay, you can see again a very high correlation, from the 1999 to 2009, okay, about 10-year range. Okay, these two, variable actually have, quite a high correlation. But again, okay, Nicolas Cage doesn't drown people, right? So, it has nothing to do with Nicolas Cage. I mean, the number of the movies Nicolas Cage, participate in. Okay, it doesn't make sense. So you can see so many such examples, are shown in this web page. Okay, this number of the per capita cheese consumption and the number of people who died by becoming tangled in their bed sheet. Okay, again, a very high correlation. Okay, for the past from 2000 to 2009. Okay, but again, this is just show you a correlation. This has nothing to do with causation. There are so many examples. Okay, I mean they are quite interesting. That can be used as your chit chat. Okay, but obviously like I don't think like you get the idea. Okay, so if you're interested in the causation relationship, okay, and also are interested in how you can build a model that incorporate causation, causal relationship, okay, then a good reference book, okay, on causation, okay, this is this book is called The Book of Why, okay, by UCLA professor Judy Pierce. Okay, Judy Pierce. I mean, he was a recipient of like a Turing Award. Okay, about a little bit more than 10 years ago, if I remember correctly. I mean, the reason he received that the Turing Award, you guys know the Turing Award is the highest recognition stood to computer scientists. Okay, so just like Nobel Prize. Okay, but to be honest, I really feel like the Turing Award is much more prestigious than Nobel Prize. Why? Because in Nobel Prize, every time something is announced, it's very common for you to hear like, okay, a group of people was like, earned, for example, like a Nobel chemistry, or Nobel like medical, okay. So they normally give like not only one person, but also a group of people, okay. But for the Turing Award, normally every year, okay, normally most of the majority of time, they only give to one person, okay. So yeah, that year, Judy Pierre won the award. Yes, he was the only recipient of the Turing Award. Yeah, and obviously, I mean, he got recognition because of his contribution to the causal model. I mean, he was able to build a model that you know discuss the the causation. Okay, I mean in addition to correlation. Okay, so of course, like most of his publications are very mathematics oriented, and they are difficult to understand. But this book, okay, the Book of Why, actually is written for general population, general people, okay, not necessary in computer science. So he tried to explain his idea in a very simple manner, okay. So if I remember, this book became like one of the best seller, okay, um, out there, okay. So I mean, if you are, and I'm pretty sure this book has all been translated into many languages, including Chinese. Yes. So if you are interested, I mean, I highly recommend this book. Okay. Yeah. So yes, as I said, correlation is useful in establishing causation. Okay, because causation obviously is one level up of correlation. Okay, so correlation is not useless when it comes to establish a causal link. Okay, a correlation can in fact support causal link. Okay, but we need to perform carefully designed experiment. Okay. So for example, if we know the global warming is highly correlated to the increasing level of atmosphere, CO2. Okay, the CO2 we want to establish. Okay, this causal relationship, like CO2 causes global warming. Okay, so from the observation alone, we cannot get what we want. Okay, but what we can do is that, okay, we can the reason we cannot do that is there may be a third variable. Okay, we didn't take into account that produce both higher temperatures, okay, and a higher level of CO2. Okay, so this may be the case, right? I mean, who knows, right? But what we can do is we can do an experiment, okay, to gain insight. Okay, for example, we could build a set of glass tanks filled with different quantity of CO2, and we put these glass tanks, okay, on like on the sunlight, okay, and measure their temperature. Okay, so if we do this, we will be able to verify the tanks with higher level of CO2, have higher final temperature or not. Okay, so hence we can conclude that indeed CO2, okay, will cause higher temperature. Okay, so you can see that in this example, Okay, we are able to establish this causal relation because, okay, we are able to control the amount of CO2 in each, glass tank, and have it go through like sunlight. Okay, but I mean, remember the example we used, like the sun radiation and the gas bill. Okay, um, unfortunately, like when you do the similar experiment, okay, try to adjust your gas bill, okay, intentionally adjust the gas bill. It doesn't affect the sunlight, sun radiation, right? So that's the primary difference. And this type of experiment has to be designed carefully. And actually, this has been mentioned in Professor Julia Pierce, the Book of Why. So just want to give you an idea, okay? The correlation, causation, okay, what they are. And if you want correlation, that's easy job, okay? Even for some observed, I mean, very, very different variables, or like very interesting variables, like remember, like the Nicolas Cage's like movie participation, and the people who drown by water. Okay, I mean, you can do the correlation very easily. Okay, but to have a causation relationship, okay, you have to find the mechanism that one changing one can affect the other. Okay, that's I mean, totally different thing. Okay, but here we also want to remind you the reality is complicated. Okay, why? Okay, we just show you the example. The CO2 contribute to like a higher temperature, right? But in fact, higher temperature will contribute to higher level CO2 as well. Okay, because oceans are a reservoir, okay, of CO2. Oceans store a lot of CO2. Okay, when the ocean is heated up, okay, the CO2 in the ocean will be released to the air. Okay, so if you ask, higher temperature, where higher temperature cause more CO2, if you are, you are in like Earth science, okay, your answer is actually yes. Okay, so higher sun radiation means more energy is delivered to home, right? Okay, so part of that energy is reflected as part is turned into heat, and part of the heat is absorbed by the house, and part of the other part is lost to the environment. Okay, so amount of heat loss depends upon several factors, such as outside temperature and the speed of wind. So there are so many factors, okay, that affect this. And also, the gas bill could be affected by other factors, such as international price of oil and the gas. We know in Taiwan, we know about that very well, right? The international price of gas or oil, obviously affect our, electricity bills. Okay, I mean, US, that's gas bill. Okay, so the cost profit for the company Okay, and obviously how greedy the company owners are, right? Okay, and also how tightly the government regulates the company. Okay, if the company is regulated by the government very tightly, then the company wouldn't be able to raise their price like arbitrarily. Okay, which is actually done in Taiwan. I mean, Taiwan actually put a very strict regulation on the electricity bill. Okay. So, in summary, life is messy. Problems are not generally simple to understand, and the context is always important. Okay. Statistical model, okay, help us to achieve better interpretations, reducing the risk of making nonsensical, okay, statements and get better predictions. But none of this is automatic. Okay. To be honest, the statistical model, okay, always simplify your problem. Okay. If you're, I mean, they do not simplify the problem. I mean, we just couldn't build a simple like statistical model. For example, okay, remember like the linear regression that we just talked about. Okay, obviously, you know, sometimes when you have so many factors, okay, in the simple linear regression, we only consider maybe one factor and disregard the other factors, right? So, but as we have said, life is messy. Okay, so problems are not generally simple to understand. So, yeah, uh, you just have to the model you build, okay, help you to understand the relationship between two variables, and they obviously help you to interpret something. But that's about it. Okay, there are so many other factors that we may not take into account. Okay, just want you to be aware of that. So by using almost identical, uh, uh, technique, okay, we can do polynomial regression. Okay, in a polynomial regression, instead of using a line to fit the data, okay, we are using a higher order polynomial to fit the data. If you still remember, in a linear regression, okay, the mu, okay, equal to beta 0 plus beta 1 x1. That's it, right? But here we could go, beyond that. We can have beta 0 x0, beta 1 x1, beta 2 x squared, beta 3 x third power of, power of 3, and so on to beta m x to the power of m. So you can imagine, okay, this formula obviously include the simple linear model in there, right? So, yeah, if you set all the coefficient, the beta 2, beta 3 up to beta m to be 0, then yes, what we are going to get is a simple linear model. Okay, so in some sense, okay, the polynomial regression subsum the simple linear regression. Okay, so yeah, but still the polynomial regression is still linear regression. Okay, because we are treating them using a linear function. Okay, here when I say linear function, you may disagree with me, but let's try to treat the x to the power of 1 and x to the power of 2. Okay, you can treat this different order of x as separate variables. Okay, if you consider them as separate variable, they look like a linear regression to you, right? So actually, like the third term, okay, I mean in this beta 2x squared, okay, the third term control the curvature of the relationship, okay, as we will, see in later, okay. So to show, like to demonstrate the this polynomial regression, okay, we could use the second nth count quartet data set, okay. The second, we use the third one, previously, to show you like the impact of outlier, and also we show you how we can, adjust our model, okay, to to reduce the impact of outlier. Okay, remember? Okay, so the second nth count quartet data set, okay, what does it look like? Okay, so this little piece of code is able to, depict the second data set for you. Okay, it looks like this. So this point looks like they are a perfect fit of a quadratic form, right? So you may wonder, so why is this data set, included in the nth count quartet data set? Okay, what does this set of this set of data, okay, trying to tell us? Okay, the nth count quartet, okay, data set, each of them, okay, try to tell a story. So this one, it tells you, okay, the importance of the complexity of the model. Okay, so if you use, for example, a very simple model such as simple linear regression, you can never create a line that capture the trend of these points, right? But with polynomial regression, we are able to do that. So how do we do it? This model is very, very simple. Okay, so obviously we have alpha, okay, and we have beta 1, beta 2, right? The beta 1, beta 2, okay, with mu 0 and standard deviation 1. So pretty much like a normal, standard normal distribution, okay. And for the alpha, we put it as like the mean of y2, because the beta 1, beta 2, okay, initially, okay, are assumed to close to 1 to 0, right? Because we try to set the beta 1, beta 2 to have the highest probability to be 0, right? So in that case, like the mean of y, okay, should be considered as like the alpha value. So that's why, okay, you can see the alpha is normal at the mean of y2 with standard deviation 1. And then, okay, we use half Gaussian, okay, for epsilon. Okay. By the way, the half Gaussian is a distribution that, I mean, let me show you. Here. This one. So this is the half Gaussian distribution, and as you can see, okay, the beta control this half Gaussian distribution. You know, you can see from 0.5, this is this line, to to the middle one. Okay, the red line, I mean, which is beta equal to 1.0, to like beta to be 2.0. I mean, it's quite flat, right? So you can see this trend, and you can imagine this trend is obviously when the beta is 5, this line is almost flat, right? So again, this indicate a very flat, very uncommittal prior for epsilon. Okay, so okay, so we put this, okay, half Cauchy for epsilon, okay, non-committal one. And then the mu will be alpha plus beta 1 times x2 plus beta 2 times x2 to the power of 2. So we are using the same x2, but to create two terms. It's obviously not a problem. Okay. And then, we try to use this normal, which use the mu is the previous one. The standard deviation is epsilon. Okay. And observe, I mean, we try to fit this with y2. Okay. And then we generate 2000 traces. Okay. So this is our like polynomial regression model. To be exact, it's with order 2. Okay. Yeah. Yeah. It's already 9:50. If you don't mind, I mean, let's take a 10 minutes break. Okay, because yeah, I think I need to um, rest my voice. Okay. Okay. Thank you. Okay, so let's get started. Okay, so once we have this model and generate the 2000 samples, and we can, draw, we can get the mean of alpha, beta, and beta 1 and beta 2. Okay, and use that to draw polynomial, I mean the parabola. Okay, which, okay, I mean, by using this piece of code, okay, we can show that it actually go past all these points pretty much perfectly, right? And you can imagine that if you do not use the polynomial regression, say you use a linear regression, this data set will pose a problem, right? Okay, because most likely your line will look like this, which will give you a wrong impression that as x increases, like the y should also become bigger because you are going to have a positive slope. But the answer is actually no, because I mean, as you can see, at the last few points, actually we have a turn, right? Which indicate like actually when x increases, I mean, we actually get a smaller y value, okay? So, and notice that, okay, the beta 1, beta 2, now cannot be explained as regression, as like like a simple linear regression, because remember in the simple linear regression we say beta 1 is like the number of the unit of x, okay, when you will be changed when you add 1 unit of y. Sorry, it should be reversed. Okay, the number of unit for y that will be changed when you add a unit of x. That's pretty much just the slope, but now these beta coefficients are no longer slopes. Okay, so beta 1 is positive. Okay, that is why, okay, at the beginning we have this going up, this value going up, and but we have the negative beta 2, okay, which eventually play bigger role, okay, when x becomes bigger. So actually when x is smaller or equal to 11, okay, the dominating contribution comes from beta 1. Basically, like y is 11, you can see, okay, the center is about like 1 here, right? So it's from here another what should I say, like from the -6 to like 11, about this range, okay, all the points will have like a positive y value. But when the x is greater than 11, beta 2 dominates. In other words, I mean, because beta 2 is negative, so we keep going down. Okay. So problem of interpreting the parameters, not just a mathematical problem. Okay. If this were the case, we could solve it by inspection and the understanding of the model. Okay. But the problem is that in many cases, the parameters are not translated to meaningful quantities in our domain knowledge. For example, the beta 1 and the beta 2 in this example may not, reflect a certain value in our domain knowledge. We cannot relate them with the metabolic rate of a cell or the energy emitted by a distant galaxy or the number of bedrooms in a house. I mean, all these are meaningful, explanation for certain parameters, but they cannot be used to explain, the models. As the model become more complicated, that's, may become an issue. Okay, so they are just knobs we can tweak to improve the fit, but without a clear physical meaning. So this beta 1, beta 2, we can tweak, but they may not have a clear physical meaning. Okay, so in practice, most people will agree that polynomials of order higher than 2 or 3 are not generally very useful models, and alternatives are preferred. Okay, for example, like Gaussian processes. I mean, the chapter 7 will talk about this, but I don't think we will talk about this in this class. Okay, because I think what we can do is we'll finish this chapter and then talk about MCMC, and then we'll finish by covering the generalized linear model. I think that's pretty much enough. Okay, so for the Gaussian process, obviously this is also an alternative for like a more complicated situation. But if you are interested, feel free to check it out. Okay, I mean from textbook. But as you can see, okay, it's meaningless to have a polynomial regression with order higher than 2 or 3. Okay, this is an important message for you. Okay, I mean, yeah, I mean it's you can always increase the the order, okay, to to fit your data point. Okay, but this may not be ideal. Okay, so we can think of the line as a submodel of the parabola when beta 2 is 0. Okay, and a line is also a submodel of a cubic model when beta 2 and beta 3 are equal to 0. Okay, so it looks like I mean, and the parabola is a submodel of the cubic one. Okay, so you obviously like the higher order subsums the lower order polynomial regression, right? So in principle, okay, we can use like polynomial regression to fit like arbitrary complicated model, complex model. That's ideally speaking. Okay, but we would just to want to build a polynomial with the right order. We could do this by increasing the order one by one until we do not observe any improvement on the fit. Or we could build infinite order polynomial and then somehow make all the irrelevant coefficients 0 until we get a perfect fit. Okay, so you can give it a try. Okay, we can start with a very simple example. Okay, we can use the quadratic model. Okay, the with order 2 to fit the third group of nth-count data set. Okay, the nth-count data set is the third one is the one with the outlier. Remember, and you can use the the quadratic model to see if you can fit that. Okay, so if you try it, okay, you have observed that it is possible to use a quadratic model to fit a line. Okay, while it may seem okay, the previous simple experiment validated the idea of building infinite order polynomial to feed the data. We should not do that. Why? Okay, because in general, using a polynomial to feed data is not the best idea. Okay, but because it does not matter which data we have. In principle, it is always possible to find a polynomial to feed the data perfectly. Okay, I mean, for example, like we know like if you have 2 points, then a linear model will always cover that 2 points, right? For 3 points, we just need to have a polynomial of order 2, right? So we can actually dictate like how the number of order required to fit endpoints, right? So this is like an easy job, okay, if you have like the high school math, right? But fitting data perfectly is actually wrong. Okay. Chapter 6 will talk more about this, but basically, okay, a model that fits your current data perfectly will do a very poor job at fitting or describing unobserved data. Okay, this is called overfitting. Okay, because like in real world, okay, the data always comes with noise, okay, and sometimes interesting pattern. So our model should try to should try to find like the pattern from the data, not try to fit like every point in the data set. Okay, because the unobserved, the data, the future ones, okay, they're because obviously, when you go past all the existing points in the data set, it means your model actually pick up those noises, right? Which are normally like affected. We normally consider those noise as white noise. In other words, it's a Gaussian noise. Okay, so if your model pick up those Gaussian noise, then it's guaranteed that it will not perform well in the future, because like the new data set, okay, the new data points, okay, could have a very different noise, okay, and also like well, the new data will generate like at a certain point, but your model, because it pick up those noise, so it assume like well, the trend is somewhere else. Okay, instead of like a simple trend, it'll try to find a complicated pattern that is actually not necessary. Okay, so this phenomena, okay, we call it overfitting, and it's actually a pervasive problem in statistics and machine learning. Okay. So it is very convenient to use polynomial regression to talk about like overfitting, because it's easy to see the problem. Okay. So these generate intuitions that we can translate to more complex models, which can lead to overfitting without, being noticed. Okay. So again, chapter 6 will talk about this stuff. Okay, but I'm not sure if we can cover that like in this class. Okay, so for now, let's assume like you guys will, check it out, okay, in the future. So, so far we have been working with one dependent variable and one independent variable, right? In the simple linear regression, or even in like a polynomial regression, we have one independent variable and one dependent variable. Okay. Nevertheless, it's not unusual to have like several independent variables that we want to include in our model. Okay. For example, okay, if you want to estimate the quality of wine, okay, wine making is a very complicated process. Okay, so the quality of wine is our dependent variable. Okay, because I drink red wine. Okay, so I know like the quality of wine is very complicated process. Okay, can be affected by many factors such as acidity, density, alcohol level, residual sugar, and the sulfates content. Okay, so the rest of these terms are what we call the independent variables. So we normally use this independent variable, which we have control over with, to predict or to determine the quality of wine. Okay, and by the way, since we are on this topic, okay, if you see like a wine has like a high level of sulfate content, any question? Sorry, I cannot see. Yeah, I don't think that's related to this class. Hmm? Oops. Sorry. Oops. Any? Oh, okay. Never mind. Okay. Yeah, it's not related to a class. Okay. So back to the class. Okay. So in case if you see a wine has like a high level of sulfates content, okay, don't drink it. Okay. Like a lot of time when you get drunk, okay, you have hangover, right? Okay. And the reason for you to have hangover most likely is caused by the sulfates content. Okay. So for example, okay, beer has a high concentration of sulfate content. Okay. So if you drink beer and get drunk, the next day when you wake up, you will feel so bad. Okay. That's the sulfate content like play into like that caused you feel like dizzy. Okay, the other part like acidity, density, or alcohol level, the sugar. They can be absorbed by our body much easily. Okay, so also student average grade. Okay, you guys are student. Okay, so this is dependent variable. Okay, and the family income, the distance from home to school, and the mother's education. So from the past study, okay, these few factors actually has a big impact to students' average grade. Okay, the first two terms, family income and distance from home to school, normally means like if you can get like the first term basically means like if you can any okay, never mind. Yeah. the first term, okay, family income dictates like how many how much resource, okay, the family can offer to the student, okay, such as like maybe like a private tutoring, okay, those type of stuff. And the distance from home to school basically, you know, say something about like, I mean, if you spend a lot of time like traveling, okay, then the number of hours you can spend on your subjects will be limited, right? And the mother's education normally like has a very important indication because a lot of time like a mother um normally take care of the kids much better. And you know, if a mother has a higher education, uh, she will um, you know, um, she will monitor the kids' progress much better. Okay, so these factors, okay, can be treated as independent variable for the student grade, average grade. Okay, and we can easily extend the simple linear regression model to deal with more than one independent variable. Okay, basically, okay, remember like the polynomial regression. Okay, I told you guys to treat like a higher order as different variables. Okay, so you can pretty much do that. Okay, so that's called multiple linear regression. I'm sorry. Sorry, got a call from family. Okay, yeah, never mind. Okay, so where am I? Okay, yeah. So this model is called multiple linear regression. Okay, or another way to call it is multivariable linear regression. Okay, but there's another term called multivariate linear regression. This represents different thing. Okay, because the multivariate linear regression means we have multiple dependent variables, meaning we are predicting more than one term. Okay, so okay, variable linear regression is different from multivariate linear regression. If you are afraid of like causing confusion, you can just use multiple linear regression. Okay, for what we have now. Okay, so in a multiple linear regression model, okay, so we model the mean of dependent variable like this: mu equal to alpha plus beta 1 x1 plus beta 2 x2 and so on plus beta m xm. Here, x1 x2 and up to xm, they are no longer just orders. Okay, they each of them represent a different factor. Okay, different factor. So um so this obviously this independent the value of these independent variables will be obtained from the data, right? But if you remember, like in the polynomial regression, we have x1, we have x, and then we have x squared, we have x cubed, and so on, right? So those variables, okay, are really computed from one single independent variable, right? So the so in some sense, we can treat the polynomial regression as a multiple linear regression, but with made up variables, because those variables like x squared, we can treat it as x2, x cubed, we can treat it as x3, and so on. Okay, so those x2, x3 they could be considered made up variables. So yeah, excuse me. So using linear algebra notation, okay, we can write it as mu equal to alpha plus x beta. In this case, beta is a vector, okay, of length m, and alpha, sorry, and x is a matrix, okay, it's a matrix. Depending on the number of terms you want to predict it, okay. In other words, the number of dependent variable, okay, it will be n plus n times n. I'm sorry, n times n. Okay, or if we have like only one dependent variable, then the x beta will look just like this. The beta 1 x1 plus beta 2 x2 plus blah, 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 plus beta m x1. So we can we can write it as like using like the first one will be 1 times m. Okay, the x will be 1 times m matrix. The beta will be m times 1. Okay, vector. Okay, and this will be just a kind of like a dot, inner dot of two. You can say they are two vectors. Okay. So using a simple linear regression, we'll get a straight line. Okay. To explain our data. So in multiple linear regression model, okay, what we find is like a hyperplane. Okay, the hyperplane, I mean, in a higher dimension that hopefully like also explain our data. Okay. So here's the thing. Okay. First, we generate our data. Okay. So we try to create like a 100 point. Okay, with the alpha value to be 2.5, beta value to be in here we have like a 2 beta because we have x1 and x2. Okay, so the first coefficient for x1 is 0.9. The second coefficient for the beta 2 is 1.5. And then okay, we create some random, values, okay, and store it in the EPS real, okay, and then here, okay, we just try to create that those 100 point using like the predefined alpha real, beta real, and epsilon EPS real, okay, and yeah, because it's like a 3-dimensional, so it's probably difficult to show on the screen, but we try our best, okay, because like we try to show two between each independent variable and the dependent variable, and the last one between two dependent variable, okay, both dependent variable. So it looks like this. X0 and Y looks like this. X2, X1, Y looks like this. And between X0 and X1, they are pretty much random, right? So this show you like the 100 points that we generate, okay, using this piece of code, okay, like although it's not like a 3D figure, I hope you get an idea. Okay, x0 and x and y are less dependent than x1 to y, as you can see. Okay, and x2 and x1 and x2 are pretty much independent. Okay, so now we can use the PyMC3 to define our model. Okay, so let's just look at the piece of code. I think that's probably easier. Okay, so alpha temp is a normal distribution with a mean 0, standard deviation 10. So you basically say like it's a very flat plier, right? We have used such a plier, I mean, several times. So hopefully you are, I mean, very familiar with what we are doing here. And for beta, it's a normal distribution with mu 0 and standard deviation 1. So it's a this is a standard normal distribution, okay? And the shape equal to 2 means we have beta 1, beta 1 and beta 2. Okay, we have two variables, okay, in beta. Epsilon is like a half Gaussian. I already told you like what half Gaussian looks like. So again, this is a very flat. Okay. So one thing interesting is that, okay, so we try to, you know, create this mu to be alpha temp plus like, you know, PMS dot. So this is like a matrix multiplication of X center and beta. Be careful about this X center. This X center actually, okay, when we create these values, we intentionally, you know, X center is the X minus X mean. So we already do like the variable shift to make the mean of X center to be at 0. Okay. So so that's why, okay, you can see that, okay, the alpha and the beta, their mean are all at 0. The mu are all at 0 because we already center the X. But, you know, so then your alpha will be, you know, this is alpha temp. So you have to add that, you know, value back. Okay, so alpha will be, you know, alpha temp minus, you know, these two, the multiplication of these two matrix. Okay, you have to add them, put them back. Okay, and then your y predict will be, you know, mu is mu. Okay, just this one, and the standard deviation is epsilon, and observe is y. You are trying to fit your data. Okay, and generate 2,000 sample. And what we are going to have, okay, if because it's the three-dimensional, I mean, hyperplane, so it's difficult to you know, illustrate, but we can generate a you know, summary of these inferred parameters, and as you can see, okay, alpha 0 is, well, we only have one alpha, okay, so it's 1.86. Beta 0 is 0.97. Beta 1 is 1.47. Epsilon is 0.47. So those are, of course, means. Okay, so you can check. Okay, for example, the real alpha is 2.5. Real beta is 0.9, 1.5, right? The epsilon is a random value, so don't worry about it. But it's between 0 and 0.5. So let's see. okay, 1.86 is a little bit away from 2.5, but this 0.97 is very close to 0.9, right? And again, 1.47 is very close to 1.5, right? And epsilon is in between 0 to 0.5, yes. So this is, is capable of recovering the correct values. Okay, this model is capable of doing that. So consider this, situation. We have a variable z correlated with the predicted variable x, and the same time, okay, with the predicted variable y. Okay, suppose that variable z is the one responsible for causing x and y. Okay, so it's do we have an example? Yeah, here Z could be the Industrial Revolution. Okay, because we know it's Industrial Revolution that caused the number of pirates and the concentration of CO2. Okay, you will see number of pirates has correlation to the concentration of CO2, but really what actually impact the X and the Y are, is the Industrial Revolution. Okay, so this example should be very familiar with Pastafarian reader. Pastafarian is kids, it's a TV series for kids. Okay, so it's not available in Asia, I think. Yeah, but yeah, you guys know, for example, in Chinese, 幼幼台, okay, or 小虎, right? Okay, I don't know the English term for that, but just like something like that. Okay, it's a made up story. Okay, for, well, apparently it's about pirates, and so you get idea. Okay, so if we omit Z from the analysis, we may end up with a nice linear relation between X and Y, and we may even be able to predict Y from X. However, if our interest lies in understanding global warming, we could totally miss what is really going on with the actual mechanism relating these variables, because we are going to link, when we link X and Y, okay, they actually have no, because yeah, they have correlation, but when you try to explain them, it'll be difficult. For example, it's just like remember the figure I show you, like a Nicolas Cage, movie, okay, versus like a number of people drowned in the water. Okay, they have correlation, but it's difficult to explain their the inter working mechanisms between these two, right? So similarly, okay, yeah, this is like the reason we omit Z in our analysis. Maybe, okay, I just mean maybe there's a factor that both impact like Nicolas Cage, the number of movies Nicolas Cage participate in, and the number of people drowned in the water. Maybe there's another factor that affect both, but because we didn't consider that factor, so yeah, we end up having such a interesting figure, right? So So we already discussed correlation does not imply causation. Okay, so one reason this is not necessarily true is that we may be omitting the variable z from our analysis. Okay, that's exactly what we just talked about. Okay, so when this happens, z is called confounding variable or confounding vector, confounding variable, confounding vector. So in many real scenario, okay, z is very easy to miss. Okay, so maybe we didn't measure it, or it was not present in the data set. Okay, or we did not even think it would be like a factor. Okay, in our problem. Okay, so basically it's just like some important factor that we didn't take into account. Okay, so not taking into account confounding variables in analysis could lead us to, establish spurious correlations. Yeah, the spurious correlations are just those relations I show you, okay, in that web page, under that web page, okay. I believe that web page is called spurious correlation, okay. So this is always a problem. We try to explain without caring about understanding the underlying mechanism, okay. So understanding the mechanism, okay, helps us translate what we really learn, okay, to a new situation. So this is more important, okay. We want to know, we want to use correlation, eventually want to be able to understand the underlying mechanism, okay. But the blind predictions do not always have good transferability. I mean, so the confounding variable is very important. It's very important. Okay. So for example, number of sneakers produced in one country could be used as an easy to measure indicator of the strength of its economy. Okay. So for example, like in Taiwan, we used to produce like the most number of sneakers in the world. Okay. But this could be a terrible predictor for other countries with a different production metrics or cultural background. Okay, some different countries, they may have a different production metrics or different cultural background that may affect their like the number of manufacturer sneaker manufacturing in their country. Okay, so this is could be a terrible predictor. Okay, so okay, again, let's try to synthesize a data set to explore the concept of confounding variable. Okay, so this piece of code simulates a confounding variable as x1. Okay, so x1 will influence both x2 and y. Okay, first you randomly, generate like some number of x1, and x2 is actually x1 plus some random variable, random number, and the y will be x1, also x1 plus some other random variable, other random numbers, and then we store this together. Okay, so one thing to notice that is that all these variables, they are already centered. What should I say, like because they are generated randomly, so it could be positive, could be negative, right? So the average of x1, x2, and y are all 0. okay, the expected value will all be 0. Okay, they are already centered. So you can see that, x1 and x and y are correlated, obviously. X2 and y are correlated as well, because x2 actually will be x1 plus a random value, okay? And x1, x2, they are obviously correlated, okay? So you can build a model, okay, using x1, x2 both, okay? So, so this is obviously multiple linear regression, okay? So here, okay, the alpha is a normal distribution with mu 0, standard deviation 10, beta 1, beta 2, okay, both are normal with mu 0 and standard deviation 10. So you can see alpha, beta 1, beta 2 have very, non-committal priors, okay? And the epsilon again is half Gaussian with beta to be 5. So it's a very flat one, okay? And then we set the mu to be alpha plus beta 1 times the first x and beta 2 times the second x, okay? And then, okay, we try to fit this, okay, using the observe, using the data set y, okay, and with like a mu to be this one, their deviation to be epsilon, okay, and then okay, we generate a trace of 2,000 points, okay. So the previous model is for, when we consider both x1 and x2, okay. And then the next example is we only consider x1, okay. So we build a simple linear regression, okay, between x1 and the y, okay. So this is even easier, right? The alpha and the beta one are exactly the same, okay, and epsilon, yeah, they are the same. And then mu equal to alpha plus beta 1 times the first x. And then, we try to fit this simple linear line, okay? And again, generate like 2,000 samples. And this one is we try to use x2 as independent variable to again to predict y. Okay, so pretty much everything will be similar, except that we use x2 instead of x1. Okay, and then we generate 2,000 samples. And then we try to plot the forest. We know like we can use the plot forest to compare like result different models, right? So so this is the result, okay, of the x1, x2, and x1, and the x2. Okay, so the mx1, x2 represent like a result from the first multiple linear regression model. The mxy means the model we get from using the x1 as the independent variable to generate simple linear regression. And the mx2 means that we use x2 as a simple linear regression, as like a independent variable and generate a simple linear regression. Okay, and obviously we can only compare beta 1, okay, between mx1, x2 and mx1. And then we can only compare beta 2 between mx1, x2 and mx2. Okay, because, well, mx1 doesn't have beta 2. and MX2 doesn't have beta 1. Okay, so well, it's 50. So let's take a 10 minutes break. Okay, we come back. I mean, we'll continue discussion. Sorry, my voice is really hurting. It's really bad. So I just have to take more rest. Okay, so let's take 10 minutes break. Okay. Sorry for the late. I mean, there's some technical issues. Yeah. So anyway, first I want to point out that this figure has some errors. Okay. Here on the left hand side, okay. For beta 1, the top and the bottom, these two should be switched. So in other words, the for the top portion, the blue result is the one comes from like MX1. And the orange one actually comes from the MX1X2. Okay. And for the lower portion, again, the top one actually comes from the MX2. The bottom one comes from the MX1X2. Okay. So there's something wrong. So you can see like the beta one for model MX1X2, which is actually indicated by the orange color of the top. Okay, it's close to 0, right? So this indicates an almost null contribution of the X1 variable. Okay, to explain why. Okay, but this is interesting because we know when we generate the data, we already know the really important variable is X1, right? But the X1, X2, okay, model, the beta 1 X1, X2 model, okay, is close to 0. Okay. So also notice, okay, so the beta 2 for model, this MX2 is around 0.55. This is actually there's actually something wrong about this explanation, but you get an idea. Okay, the so the most important thing is the information in X2 is redundant given X1. Okay, some explanation here is wrong. Okay, and I actually have it corrected. Okay, and for the figure, because it's a figure, I cannot make correction. Okay, so I want to tell you, okay, something is wrong with the figure. Okay, and this explanation also I try to fix the part that I can rationalize with. Okay, so the first half, I mean, it's obvious in the case. The second part, starting from also noticed, I mean, this is obvious not the case, not around 0.55. I don't know, like, I mean, this is the error in the textbook, but basically this tells you that, okay, when you have an extra variable, okay, in your model, okay, so because like MX1, X2 obviously has like 2 variables, okay, 2 independent variables, but these 2 independent variables are somewhat like correlated, right? So the result is going to be like difficult to explain. Okay, so this is because X2 is redundant giving X1. Okay, so this is going to become even more of an issue when your data set is like even more highly correlated. So here, okay, you can see that, okay, so this again, we try to generate another data set, okay, with 100 point. Okay, everything are very similar to what we have previously, except okay, where is it? Yeah, basically you can see from here, okay, we replace this x2 statement equal to x1 plus blah 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 with like this commented statement x2 equal to x1 plus blah 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 with a scale with a random number much smaller than the previous one, indicating that x2 is even more like correlated with x1 because obviously like the random number you added to the end of x1 decrease, right? So the other part remains the same. And then, as you can see that x1 and y, the relationship between x1 and y and x2 and y are still the same. But relationship between x1 and x2 are almost a straight line, indicating that they are highly correlated. Okay? So if you try to use this to create a multiple linear regression model, okay? And generate 2,000 samples. I mean, this piece of code is the same as, pretty much identical with the like what we have previously. So I don't think we need to explain. So you can see that, okay, the beta 0 and the beta 1 are very, very wide. Okay, the HPD for beta coefficient is suspiciously wide. It is because one can be used to replace another. Okay, when one increase, the other one decrease. But because they are highly replaceable. Okay, and if you try to output the beta 0 with the beta 1, you can see that. Okay, when one increase, the other one decrease. Right? So this is an indication that one of them is a confounding variable. Okay. So marginal posterior for beta is a really narrow diagonal. Okay. When one coefficient goes up, the other will go down. Okay. Both are effectively correlated. So it's just a consequence of the model and the data. So according to the model, I mean, we have this. But if we assume x1, x2 are not just practically equivalent, but mathematically identical, okay, then you can, rewrite the top formula into like this, right? Because x1, x2 are the same, right? In this case, you can tell because the sum indicate one value, right? But you do not have like any restriction on the beta 1 or beta 2. When beta 1 increase, beta 2 decrease. When beta 1 decrease, beta 2 increase. Because we only, the data only restrict this, this simple linear regression. Okay, so that's the reason. Okay, that's the reason the beta 1, beta 2, has such a, wide HPD. Okay, which is not supposed to happen, okay, in a regular situation. So when this happens, okay, we say the model is indeterminate. Okay, So, or the data is unable to restrict the parameters in the model. Okay. So in our example, there are two reasons why beta cannot freely move over the negative infinity to positive infinity. Okay. Because like both variables are almost the same, but they are not exactly equal. Okay, so still there are some variable, randomness in there. Okay, and second, and most important point is that we have a prior restricting the plausible value that beta can take. Remember, in this model, the beta is a normal distribution with a mean 0, standard deviation 10, right? Even though this is a very weak prior, it still plays an important role in restricting this range. Otherwise, it will be even wider. And you can see that, okay, the range is, goes from -10 to +10. It's pretty much like, indicating the range of the, indicating like the standard deviation of the Gaussian, the normal distribution for the prior, right? So it's not like something like that's happen accidentally. Okay. So there are a couple of things to notice. Okay. First, the posterior is just the logical consequence of our data in the model. So there's nothing wrong, okay, with obtaining this wide distribution for beta. Okay. Stella V, in English, it means this is life. Okay. So, well, that's it. Okay. So second, we can rely on this model to make prediction. We still can, even though this model is, as I say, this is indeterminate. Okay. But still, we can use this model to make predictions. Okay. If you try to run a posterior predictive checks, the value predicted by the model will, cover the data pretty well. Okay. In other words, the model is capturing the data very well. Okay. And the third, we may not be a very good, this may not be a very good model to understand the problem. Okay. Because like, it may be more clever just to remove one of the variables from the model. In other words, like keeping just one, maybe x1 or even x2, okay, will be a much better model. Okay. Of course, I mean, eventually, like in this particular example, keeping x1 is more meaningful, but that's because we know we generate x2 from x1. Okay. We generate x2 and the y from x1. But in reality, we may not know. Okay. So we'll end up having a model that predicts the data as well as before, but with an easier interpretation. At least you have only one independent variable. Okay, so it's supposedly easier to explain. Okay. So how large correlation of two variables will become an issue? Okay. So in a real data set, correlation are going to exist for some degree. Okay. So how strong should two or more variables be corrected, to become a problem? Correlated to become a problem. So basically, okay, if two variables have very high correlation, for example, like a 0.9, then it's always a problem. Okay. And the problem with this approach is that what really matters is not the pairwise correlations we can observe in the correlation matrix, but the correlation of the variables inside a model. And as we already saw, variables behave differently in isolation than when they are put together in a model. Okay, so I mean, what is an example? Okay, for example, like in the that A group example. This one. Okay, if they are put into group, okay, then I mean, if we do it separately, I mean, they show different analysis result, right? Especially the last group, right? So this is like more important. Okay. So two or more variables can increase or decrease their correlation when put in the context of other variables in a multiple regression model. So as always, careful inspection of the posterior together with the iterative critical approach to model building will be recommended, okay, and can help us to spot problems and understand the data, okay. So I think I will stop this here today because I'm really feeling not well. Okay, so starting from next because like I already up to like another like close to 50 slides. So I'm pretty sure I will finish up this chapter and next time and go talk about MCMC. And I believe I already have the MCMC slide uploaded to the course website. Okay. So the E class, I'm sorry, to the E class. So please remember to download that slide, okay, before our next lecture. And also remember, I will post the term project, and please try to find your roommate, I mean project like a members, okay, to work with, okay, as soon as possible, okay. Yeah, I guess that's it. Yeah, sorry for cutting the course short because I'm losing the voice. Okay, thank you. Okay, bye.